In this video, I'm going to explain how you solve this thermal physics question. In the scenario we're given here, we have a beaker of water into which a piece of ice is placed. The ice is of mass 0.02 kilograms and the water is of mass 0.25 kilograms. We also know that the initial temperature of ice is 0 degrees. So when it's placed into the water, it is at 0 degrees Celsius. And the water is of temperature 80 degrees Celsius. We're also given information about the specific latent heat of fusion of ice and the specific heat capacity of water. We're also told that the ice melts completely after being placed, and we must find the final temperature of the water. So before we start solving, I think it's important to understand the concept behind, because that's going to be key to solving this question. So we're told that the ice melts completely, and we're also told that the ice initial temperature is at 0 degrees. So looking at this graph over here, I have temperature versus time, and this is the temperature of a particular substance or the atoms matter, you could say. And we see that there is an increase in temperature of the matter, but then there's some stability, increase, stability, and increase. And what this actually is representing what state a substance is in. So this initial upward gradient would indicate the fact that this substance is a solid. But over here, we see that there is a plateau, almost a flat part of this graph, where the temperature isn't changing even though time is progressing. Now we're assuming that constant energy in terms of heat is being supplied to the matter. So there must be some reason as to why temperature of the actual matter is increasing. So if we look at the definition of temperature, temperature is essentially the average kinetic energy of the atoms. Let me just write that again. So temperature is just the average kinetic energy of atoms, you could say. However, when changing state, the potential energy of a system increases. So while energy is being supplied and the total energy in the system is increasing, and we know that total energy is just potential energy plus kinetic energy in this case. So while energy is continuously being supplied to the system and the potential energy, the total energy is increasing, the potential energy increases as the atoms are being drawn away from each other as it transfers from a solid to a liquid, while the kinetic energy is still the same, as all of this increase in energy is going towards the potential energy. I should write that again. That is not ET, that is EP. So that is why we do not see an increase in the temperature over here. However, we know that as a substance is changing state, the temperature stays constant. Now, it is also common knowledge that the melting temperature, or the temperature at which ice melts, so the melting point, is 0 degrees. That means that as the ice is being placed into the beaker of water, it is either just started the melting process, or we can assume that it's just starting the melting process for this question. So the first thing we need to do is to calculate how much energy the ice has absorbed, how much heat energy the ice has absorbed as it melts. And then we use the equation Q is equal to ml, because the ice is changing state from solid to liquid. So Q here will give us the energy, M is the mass, and L here is the latent heat of fusion of ice. So we can sub in these values. So I'm going to name this Q1 as well, and you will see why later on. So subbing in our values, we know that so Q1 is equal to, we need the mass of ice, which is 0.02 kilograms. So 0.02 times the latent heat of fusion. Now keep in mind, in this situation, the units are all for so the units all have the mass as kilograms. However, it should be noted that sometimes the mass might be given in grams and you'll be asked to convert, or something like that may occur where you have to have a conversion of units. So be on the lookout for that. So here we need the specific latent heat of fusion of ice, which is 3.3 times 10 to the power of 5 joules per kilogram. So 3.3 times 10 to the power of 5. Putting that into the calculator, we get Q1 being equal to, let me just double check this. Yeah, we get 6,600 joules as Q1. Now, this heat energy has to have come from somewhere. And we assume that after the ice is placed into a beaker, there is no external energy or energy from surroundings that is actually helping the ice melt, or external, the surrounding energy is what's being absorbed by the ice. We assume that all the energy that the ice is absorbing is coming from the water that it is in the beaker. So then we equate Q1 to mc delta T. Now this is another equation. There's a difference between these two, because this is for when there's a change of state. The one on the right and the one on the left is used when the substance is in a single state or in the same state. However, there is a change in temperature. Now, because we know that this much energy is being absorbed from the water, we can equate 6,600 to the mass of water, which in this case is 0.25, excuse me, 0.25 times C. C here will be the specific heat capacity of water, 4,200 joules per kilogram per Kelvin. So 4,200 times delta T. So delta T here indicates the change in temperature. T is temperature and delta indicates a change in the value of the variable. Rearranging this, we get delta T is equal to 6,600 divided by 0.25 times 4,200. And this gives us the answer of, let me just put this into a calculator here, 4,200. This gives us the answer of 6.29 degrees Celsius. So we know that the change in temperature of the water is 6.29 degrees Celsius. Now, because this heat energy is being taken away from the water and into the ice, we know that as heat energy reduces, the temperature reduces. So therefore, this 6.29 is essentially a negative as the temperature is reducing in the water. So now we have ice, or actually I should rewrite this. We have some water at 0 degrees Celsius, because remember, the ice over here has just converted into liquid, but as we mentioned over here, in the conversion process, there is no increase in temperature. So we're assuming that the ice has melted, but it's still at 0 degrees Celsius. So we have some water at 0 degrees Celsius of mass 0. Let me just change color again. 0.02 kilograms. And on the other hand, we have some more water. I'm going to use a different color for this actually. I'm going to use red. We have some more water which is warmer at 80 minus 6.29 degrees, which gives us, so that's going to give us 73.71 degrees Celsius, and that is of mass 0.25 kilograms. Now, obviously, we know that whenever there is a difference in temperature, there will be some form of transfer of heat energy until equilibrium or thermal equilibrium has been achieved, which is when the temperature is equal. So now we know that both of the substances are water, so they have the same specific heat capacity, and we know for the fact that they're going to reach the same temperature. So to figure this out, we're going to equate both sides. So we have M1C delta T1 equal to M2C delta T2. So on this side, we have the mass 0.02 times C, which is 4,200. And now here, we don't know what the temperature changes. We're trying to figure that out. But we do know that the starting temperature over here is 0 degrees. And given that the other, the other component of the water is of a much higher temperature, we know that the temperature of the solution is going to increase as well. So we're going to name that variable X. So X represents how much the temperature of this component of water increases. So this equals M2, which is this water, which is 0.25 times 4200, which is the same over here. Now, again, we do not know the final temperature of water. However, we do know that if this component of water increases to X degrees Celsius, this must decrease to T or minus X. Now T here refers to the temperature inside, so we can actually not use T, and we can directly write 73.71 minus X. Now we can cancel these two out, and to rearrange for X, we can do as such. So 0.02X is equal to, now we do some slight calculations. We can expand the bracket that we have, given that we cancel up 4200, we can do 0.25 times 73.71, and that gives us 18.43 minus 0.25x. Bring it all to one side, we get 0.27x is equal to 18.43, and then rearranging x is equal to a certain temperature, which is 18.43 divided by 0.27, 68.26 degrees, or in three significant figures, as is the norm, 68.3 degrees Celsius. And that is the final temperature of our solution that we have found for this question.